attendance, but communicate it properly, because we belong to different languages, and by the way, if you miscommunicate, if you use a wrong word instead of the exact word, it gives altogether a different meaning, and that will have a different implications later. So don't take that for granted that anything can be spoken in the lab or class. Okay, it's just my suggestion, guys. I mean, don't feel bad about it, but I'm saying if you have definitely any questions or anything that related to the lab, or you're welcome to ask. But the only thing is communicate it properly. That is what I'm saying. What exactly in your brain, first put it into proper words format, and then only you speak. That is the only constraint. Okay. What is the class thing? So the instruction from yesterday's CRC meeting was, Jayesh, as you said, there is no point in asking the students to attend the classes, but unfortunately they are making it mandatory. I'm also of the same opinion that I mean, at this age, we should not be forcing the students to please attend the class. I'll be teaching something very interesting. These things are not required, because you're all grown-ups now. If you get married, you'll have two sons, two girls. So you're of that age. So I don't want you people to actually be forced to attend the classes, but somehow the management thinks otherwise. And Kalyan, you tell the students that, I mean, you take care of the attendance. I cannot do that. You think? Please take care of that. Every day you take attendance, put in an Excel sheet or something, and then whoever is absent is all. Please let me know by every month. Can you do that, Kalyan, for myself?
Yes, sir.
Please don't mind. I am really bad at those things. Okay, so because I don't believe in that. It's not that I cannot take attendance and I can put in a lemon that I can do, but I don't want to do that, because if I see that someone is not attending, getting taking action or taking cut-off marks and all, I personally don't like, because at this age you are some of the cream in the country. You've been brought from after having filtering you through your through very difficult test and all. So I expect you people to actually be very responsible at this age, and if someone is not, that is their problem. People may say that we have to mentor and all, but 17, 18, you are grown now. You are getting your vote, this thing right also, vote right also. So you are matured enough to understand where will you go if you don't attend the classes, if you are not regular. There may be some students who are very good, even though they cannot attend, they can study on their own. They are perfectly all right for me. It's not that you have to listen to what I say in the class and you have to exactly follow what I do. Sometimes the teacher may go wrong also. The student is better than the student teachers also. That can also happen. So it's not that I'm not, I don't believe in those things. So just that's the reason why I tell you, just take that attendance. So that is one thing. Now 63 out of 84. Okay, let's start the class for today. So any doubts in yesterday's class can be, if you have any doubts. Yesterday I have some other thing, so I could not actually teach you that class yesterday. So anyone, have you solved this problem on your own, the A part? Please be answered. If you haven't answered, if you haven't solved also, that's not a problem. Just tell me. That's what I want. So this problem is very simple problem where we have given a specific gravity.
Sir.
Yeah.
Screen is not visible.
What happened?
Screen is
all white, sir.
I don't know what was the problem, but somehow, unless I switch on to my entire screen, my slides are not visible to you. Now is it visible? I think it should be.
Yes, sir.
Yes, sir. Yes, sir.
That is not the problem. I don't know what is the bug, or I have to update or what. Okay, so now any questions related to yesterday? Anybody? Please be free to ask. Let me record the case. Please don't be silent and talk something. If you understood it, say that. Just
sir, you haven't shared the slides.
That's true, but whatever you heard, you might remember, right? Don't you remember what was taught in the last class? That's fine. If you don't remember, also that's fine. So I was talking about the working principle of the dead weight tester. Have you understood the working principle, how it is working for a calibration of any pressure instrument? Yes or no? Just for your sake, you tell me. Somebody, if you don't wait for others, just those who has understood, at least they keep quiet, and those who never understood, you can say that I haven't understood. Okay, at least I can send the link. Please don't do so. Or those who understood, they say yes, one or two, that's fine. We'll go ahead. Okay. Can I take that you understood that? And then the YouTube manometers, the manometric fluid where we are using and balancing to find out the differential pressure. Have you found out that? Have you understood that? So please,
Yeah, yes, sir.
yeah, I request you people, don't be silent. I mean, it doesn't make any sense to me. Please, you are very, you are talking a lot in the previous classes. Just don't go into that. I mean, whatever you want to say, you tell from your side. Don't wait for others to answer and then. Okay? Have you understood? That's fine. If you are not understood, I can recap once again. No need?
No, sir.
Okay, fine. So we have ended up solving two problems yesterday. So one is this problem: a YouTube manometer employs a special oil. So there is a specific gravity given. Okay, you are using a YouTube manometer where the specific oil, which is having the 0.82 specific gravity as the specific gravity as the manometric liquid. So one end of it is exposed to atmospheric pressure of 740 mm of Hg. So the atmospheric pressure is 740, and the difference in column heights is measured to be 20 centimeters plus or minus 1 mm. So the difference when I found out that is when the pressure difference is in a 20 centimeters, I am finding a deviation of 1 plus or minus 1 mm. Okay, this is the deviation for 20 centimeters. So and he's also given when exposed to an air source at 25 degrees centigrade. It is mentioned the temperature also. What is he asking is, he is asking us to find out the pressure differential in Pascal. So P minus P atmosphere is asking, and then the uncertainty. So what is the uncertainty at that pressure difference? Okay. So whatever the pressure that you are having, that you have to convey. That is what he's asking. So now what we need to find out is, first he has given specific gravity of 0.82. And at 25 degrees centigrade, you know what is the density of air or water, density of water you can take. And you know that specific gravity is nothing but, this value is nothing but density of the oil by standard density of the fluid, which is around 996. Okay, you have to be very careful at the extra data that is given in the problem. So don't just forget about this data. So it has mentioned specifically that air source at 25 degrees centigrade. So you need to understand. So what is the temperature of the standard water also? At that time, we should consider 25 degrees centigrade. And when you consider 25 degrees centigrade, it is not 1000. It goes to 996. Okay. So 996 into 0.82 will give you something. Okay. So it's not 820, it's around 816.7 will come. Okay, now we found out the density of the fluid, or rho m of the fluid is equivalent to something. And then you also need to find out one limb of the atmospheric pressure he has given. So what you know is P1 minus PA is equivalent to rho m GH, right? So when you substitute that thing, P1 minus P atmosphere is equivalent to rho m, that is a manometric, into G 9.81 into H. H is the difference of this 20 centimeters, which is converted into meters. You will get into whatever you are calling it as your pressure, total pressure. Okay, up to that you are clarified, right? So next one is, what is asking is, what is uncertainty that you need to find out. So here for 20 centimeters, he has given it to 1 meter, 1 mm. So for 100 centimeter, how much it is? So that is what you are trying to find out, the percentage. And then for 100 mm, you are finding out that, so that percentage has come. Now you have to convert for the total pressure. What is the error in what is uncertainty for that, based on that percentage of uncertainty. Okay, so if it is 5% or something, then you can find it. So that will come around somewhere. So I'm trying to show you the solution for this. Now you can see over here. So the density is the special oil, specific gravity of special oil into density of water at 25 degrees centigrade, 0.82 into 996, it's 16.7 kg per meter. And then you have to find out the density, gas constant is given, temperature is given, right? Pressure we are converting. So P atmosphere is 740 by 760, which will be coming around 98,632, 4.2. In terms of pascals, if you find out, this is the pressure. So therefore, air density, if you want to find out from the ideal gas equation, we will find out that it is 1.15, because we are actually rho m minus rho f, the fluid that you have to take out, what is the applied pressure of the fluid. Because the question what it is given is, we are finding out atmospheric pressure, and other source is air source. Therefore, you have to find out the density of air, okay, P air, that is 1.15. This we have got from finding out the actual pressure in pascals, and then we are converting that into, we are using this ideal gas equation to find out this. And then you have given the column height as 0.2, so substituting everything, rho P minus PA is equivalent to rho m minus rho f, that fluid, into G into H. So that is giving around 1598.5. If you put 9.81, it will be close to 1600, whatever it is. So whenever you are solving such problems, please mention these things clearly. Okay, so uncertainty calculation, we can find it as straightforward. It is the same as the percentage uncertainty in the column height. So if you find out the percentage uncertainty, whatever the percentage variation in the height, the same will be conveyed in terms of your actual pressure difference. Therefore, so the percentage difference in height is, for 0.2 it is 1 mm, that is 0.001. For 100, how much? It is plus or minus 0.5%. So the pressure difference error will be nothing but delta P will be nothing but plus or minus 0.5 into 100 into whatever the pressure that we have got, our pressure difference, that will be this. So that is basically your 7.99, which is around close to plus or minus 8 pascals. So that is what the problem is. So I think you are clear with this. And then the second problem, we have already solved it. When it is 3 degrees centigrade, we have to find out the height h is equivalent to the x cos theta or h cos theta with the inclination, based on the inclination. So from that, you got the pressure difference of 1596.3. When it is vertical, cos 90, when you are using, you got 1598 point something. So the difference is, systematic difference is 2.2 pascals because of this mounting. So I think you have got this problem. Okay. Now today in our class, now what you have to look at in solving while using the U2 manometers are the accuracy factors. So even when you are using the dead weight tester, you have to be very sure. You have to be very sure about these following factors. You have to be very careful about these following factors. So number one is the gravity. Suppose if you are testing your pressure gauge at one place where the gravity is different, and you are taking it to some other place where the gravity is another thing, and then we will get some error, because the gravity will have some of the effect on this. Okay, so because the force it's generated by the weights will change. So that reason being, whatever the force is generated because of the weights will automatically change. So therefore, the local gravity has to be the same when we are following the things. When we are following these two things, all right. So when we are doing calibration, that means you have to do that calibration at the same place where you are actually using your experiment. Am I clear? So you cannot do calibration in India and then go to Arctic and Antarctic poles and use the same calibration, because the gravity differs there. Okay, second one is the pressure coefficient. The effective area of the dead weight tester will change with pressure due to expansion and contraction of the piston and cylinder at different pressures. So this is also one of the important thing where we are having the effective area of the dead weight tester. What will you use the effective area? So you are keeping the weights, right? The base. How do you change that? Okay. So the area values, you have to be accurate, because they may expand and contract at when using different pressures. Okay. So That means when you are changing your weights on the piston base, your area will not be constant. They're kind of varying because the pressures we are using is different. Okay? And the third one is the tear force, we call it as. So if you are not finding the force error properly because of the mass of the weights, we have this tear force error that will come into pictures. Okay. What is the piston and cylinder and carrier weights you are carrying out? They should be proper. Okay. We have to find out a characteristic of the dead weight tester to eliminate this tear force. Fourth one is the horizontal leveling of the instrument, where if the dead weight tester is not in level with the horizontal plane. Okay. So therefore, the piston cylinder is not perfectly upright. Therefore, obviously, there will be frictional force that will be falling in the piston cylinder element. So that will create extra friction, and therefore the readings will not be correct. The next one is air buoyancy. Sometimes air pressure and humidity will affect the density of air, which contributes a relatively small lifting force to the weights. So suppose if you are trying to do the same calibration at a different places and where the pressure and humidity are also different, that means the environment should be the same ultimately. That's what is being forced here, the effect of gravity or the air buoyancy. So what they will do is, because of the moisture and all, it will create a little force which actually lifts the weights, and therefore some error may come into it. Fifth one is the thermal expansion. So because of temperature, there may be expansion and contraction because of the variation. So therefore, you have to take care of the effective area of the dead weight tester, because without our knowing, it may expand due to extreme temperatures or low temperatures. It may contract. So in that sense, you have to be careful while calculating the effective area. What area you have to take, you have to be very careful. Next one is the surface tension. For fluid-filled dead weight tester, a surface tension force is exerted on the piston, right? So this surface tension force depends on the type of fluid used and the circumference of the piston. So straightforward. It will also have some surface tension effects on the measurement. So you have to be careful of considering them in the measurement. Last one is the height difference. If the dead weight tester is used at a different height of the unit being tested, force will be generated due to the head of air or fluid in the connecting tissue. The same point, what they are saying is, wherever the best practice is, whatever height you are calibrating the instrument with the dead weight tester, conduct the experiment also with the same height, because unnecessarily a force will be generated which is actually due to the head of air or fluid in the connecting. So that will create some kind of an error in the dead weight tester. Now let us move on to the next topic, what we call it as dynamic response of pressure measurement system. So far, what we have seen here in the previous section are static measurement of the steady state measurement of the pressure. So we are actually waiting for some time after the measurement started. So we will not take immediately, but we will wait for some time, and after that only you will take measurement. So that is basically your steady state measurement. But how does these measurement systems behave in the transient? So what is the dynamic response based on time, how it will be responding? So for that, I'm giving you a small example of a simple instrument, what we call it as the YouTube manometer, where your transient responses, they will be depend on, number one, the response of on what factors it depends. One is the response of transducer element that senses pressure. Response of transducer element. So it may be a sensor or whatever. The first element which actually senses the pressure, it depends on the response, how good it is, how sensitive it is. Okay. If it is very sensitive, for a small change of input, it will give an output. So depending on that, its response will vary. Second one is response of pressure transmitting fluid and then tubing. So whatever the fluid that I'm using within the instrument to transfer the signal from that sensor and continue to the other end. Okay, and what is the tubing, what is the interaction between the fluid and the tubing? Okay, what is the how this is actually supporting the transformation. Suppose if you are giving a heat input to this, some of the heat gets dissipated. It is not continuously transmitted to the instrument, to the other way. I'm just saying an example. Okay, if you are giving some temperature input, let us say that it is something that can be traveled through liquid. So if the heat is dissipating through the tube, so it is kind of distracting the information, right? It is kind of transmitting the distribution with a with an error. So most of the information that the fluid knows here will not be carried until here. Okay, some of that got wasted to the environment. I'm just telling you as an example. So therefore, the other factor which actually affects the transient response is the pressure transmitting fluid and the tubing. So we will be just looking at a U-tube manometer. So in which the manometer fluid, whatever we are taking is incompressible, that is the assumption, and the total length of the fluid manometer remains fixed. So the length of the total, not the variation in the height, from here to here, if you take it in a linear line, the length of this column is L, total length is capital L. And the difference in these heights because of the difference in the pressures is capital H, let us say. So now let us understand what are the pressures that will be applied on the liquid column L. Okay, when pressure delta P is applied, so what can be the forces that will be acting? Okay, what are the supporting and what are the opposing factors for the pressure? So the forces acting on LR, on the liquid column L, what are the pressure forces that will be acting? Number one is the force due to acceleration of the fluid. So because of this acceleration of the force, there is some force that is being applied. So you are connecting it to a tube and the water rushes with some force because of the acceleration. So it kind of the force due to acceleration of the liquid. Because of the acceleration, there is a force that is being introduced into the system. Correct? Agreed? And the second one is force supporting the change in height. So there is a force which actually creates the change in height. Okay, that is a force that is, I'm taking it as Fs. Okay. The third one is force opposing the change. Again, there is inertia to the liquid which actually tries not to change the level of the liquid, which are like opposing the changes because of the force. That is, one is the weight of the column. So the weight will balance, or it tries to stop, it tries to balance the force. The other one is the frictional forces due to viscosity. So what is the friction that is happening along with the tube and liquid as well as the liquid layers itself? This will also kind of oppose the fluid. So the more the viscous the fluid, manometric fluid is, the more opposition it shows for the force. Okay, it will not easily move. It will not easily show the difference in the heights or vertical height. So now when you apply the Newton's law to the moving manometer liquid, so what can be the variation is, number one is the force due to acceleration of the liquid is equivalent to Fs, that is force supporting the change in height. So there is a force which is actually supporting the change in height, and then you also have an opposing forces like W and viscosity. W and viscosity are the forces which are actually trying to change the. So this is the basic expression that we have. Fa plus Fs minus W minus Ff is equal to 0. The energy balance can be. But if you look at force due to acceleration of the liquid A, the total, this is what I want to find out. Okay. So what is the force that it is creating is equivalent to the supporting the change. So whatever the force that is applied minus W, weight of the liquid, minus frictional force due to viscosity. So this is the acceleration force which is actually creating this. So now let us see what is the governing, how do we define each of the terms, right? So are you understand? This is what I'm trying to find out. Because of the rushing of the fluid, because of the high change in velocity of the liquid, it is creating some force. And that force is basically, one is actually trying to change the length, and the other one is its weight which is opposing, and the other one is viscosity which is opposing. Therefore, the force due to acceleration of the liquid A is equivalent to the force which is supporting the change in height, because of the height, whatever the force are it's creating the change in height, minus W opposite force, F opposite force. So let us look at one by one. So the first one is FA, that is the force due to acceleration is given by M into acceleration, right? Can we take it as M into A? So what is mass into mass is basically density by density is equivalent to mass per unit volume. Therefore, mass can be replaced by density rho m into volume. What is volume? Area of the tube into the length. So that is the volume of the liquid, right? So that is what I have written. Rho m al, that is m, into whatever d square x by dt square is equivalent to nothing but your acceleration. Now, so acceleration is equal to dv by dt, velocity is equivalent to the distance by displacement by the time. So it is nothing but d square x by dt square or d square h by dt square, whatever it is. So the definitions are written over here. Okay. So I have defined the first thing, that is the force due to acceleration of the fluid is equivalent to rho m a into L, that is my mass, into d square x by dt square, which takes care of the acceleration. So Newton's second law I have written. So next one is Fs into A. What is the force which is actually creating that change? It is nothing but the pressure, right? Because of the pressure that is happening. So pressure is equivalent to, the change in pressure is equivalent to the force per unit area. So I am writing it Fs is equivalent to the area into delta P. Agreed? Okay. So delta P is Fs by A. So I am taking Fs is equivalent to A into whatever the pressure difference. That is what is actually creating the change in height. So I have defined Fs. Next one is W, the weight of the body, which is nothing but, as we have talked about, m into g is my weight. So therefore, rho m into Ax into g, that is what is actually created that the weight of the liquid, where it has a change is rho m A into x, whatever the difference, or h, whatever the difference that we are taking, that weight of the liquid. And viscous forces, you know, this is like the acceleration into delta Pf, okay, where this pressure difference is due to the frictional force. Okay, how do you find out the frictional force? In your fluid mechanics, if you remember, we have used Hagen-Poiseuille's law, flow law. So where you are finding out the equation for delta P, right? If it is a fully developed flow, what is the pressure difference, or what is the friction across the pipe? For a fully developed flow, you are giving it by Hagen-Poiseuille's equation. So that delta P of F is what is being incorporated over here. All right. So what we are trying to do is, I am trying to find out what is the delta PF. Okay. So for a fully developed laminar flow, with an assumption that the velocity in the manometric fluid is very small, therefore it's laminar. So when it is laminar, the volumetric flow rate written in terms of pressure gradients, you know how do we write? This is the Hagen-Poiseuille's equation, which says that pi d square by 4 into delta P by 128 mu L. This is a standard equation for a laminar flow inside a tube when the flow is fully developed. So here the diameter of the tube is lower. So the velocity of the manometric fluid is also lower. Therefore, purely we can take a laminar flow. Therefore, we can use this Hagen-Poiseuille equation for delta PF. Delta PF is equivalent to Q into 128 mu L by pi into d square by 4, pi d power 4, where d is the diameter of the tube. Okay. So now here mu is the dynamic viscosity of the manometric fluid and d is the diameter of the manometer. So now what happens to the mass flow rate? What is the expression for mass flow rate? Mass flow rate expression is nothing but Q is equivalent to area into velocity. Okay. So your area into velocity will come into picture. So therefore, you are writing like mass flow rate is equivalent to rho m pi d square pi d power 4 into delta PF by 128 mu L. Okay, so this is what its mass flow rate we are getting. Rho AV mass flow rate is equivalent to rho into AV. Sorry, mass flow rate is equivalent to density into area into velocity. What is area into velocity? That is basically your discharge. So that discharge is given here. Okay, this discharge I'm substituting there with the multiplying with the manometric density of the manometric fluid. Sorry. So rho A into V, which is equivalent to rho into Q. That is my mass flow. So that is the difference. So when the discharge is multiplied by the density of the fluid, we will get the mass. Therefore, delta PF in terms of mass flow rate, if you want to give, m dot 128 mu into L by rho m pi d power 4, where mu is the dynamic viscosity, d is the diameter of the pipe. So we got equations for everything. So whatever the term 128 mu L by rho m pi d power 4, this term I am taking it as the resistance due to friction. Okay, just to simplify the things, I'm just taking this as a resistance, or R, m dot R, which is nothing but my fluid resistance due to friction. So from the equations, what we can write, what is the force here? We have defined this force due to friction as, or viscosity as, like Ff is equal to A into delta Pf. I found out delta Pf in terms of mass flow rate into resistance. So A into R, capital R into m dot. That is what I have written. So that is what the same thing, where R is my 128 mu L by pi d power 4. 128 mu L by rho m pi d power 4. So the same thing I have written over here, A into m dot into R, where m dot can be also written as mass flow rate. You can always written as rho m A, that is rho m A, rho A V. So it can also be written as density of the manometric liquid into area of the tube into dx by dt. What is the variation with respect to time? That will give you the mass flow rate. So now substituting this 9 into A expression, we will get the force as rho m A square R dx by dt. Okay, clear? Are you with me on this? Up to this, no doubt, I guess. So I'm just trying to balance the energies, nothing more. Okay. So applying Newton's law to the moving manometric fluid, we have, as I already discussed, what is the force that is applied due to the acceleration of the fluid? Ff equivalent to the force which is actually creating the difference, which is the pressure force, minus the W, weight of the fluid, minus the frictional force, which is actually opposing the movement of the fluid. Using the whatever the equations that we have got, Fa, which is nothing but the force that I need to find out due to acceleration, that will be given by mass into acceleration. Your mass is rho m into Al. Okay, this is the mass flow rate into d square x by dx square. This term defines the acceleration. Fs, this is nothing but your pressure force written in terms of pressure difference into the area. Weight is basically written as rho m into A into, here it is, you imagine h to be x, ax into z, or whatever x difference, whatever it is creating. It's a variable. Here it is mentioned as a constant h, so it's just a weight. Minus Ff is the rho m A square dx by dt. Once we rearrange everything in the equation here, whatever we are rearranging, rho m by A, if you are kind of differentiating, because rho m A is the constant over here and here. If you rearrange that, you are getting an expression like L by G d square x by dt square. So second order polynomial term, AR by G into dx by dt. This is one constant. A d square x by dt square plus B dx plus dt plus x is equivalent to delta P by rho m. Second order polynomial kind of an equation we have got. Okay, this is kind of a constant. So therefore, we are defining here 1 by tau, which is equivalent to characteristic time. We are defining it as 1 by omega n, which is basically your natural frequency. So natural frequency and the time period are inversely proportional. Therefore, from that I can write down that it is basically square root of L by G. Correct? Okay. So, and the damping ratio, if I can write, I'm trying to define two terms over here. One is the time period, characteristic time or time period, which is the inverse of natural frequency here, which can be defined by rho L by G. So tau, I am defining it as square root of L by G. And damping ratio, again, I am trying to rotate by AR by 2G tau. A into R by 2G into square root of L by G. Okay. So that is what I am trying to. And now that above the previous expression where you have L by G, you are having this value. I am L by G. I am trying to mark it as tau square, because tau is equivalent to square root of L by G. So therefore tau square is L by G. So tau square dx by dt. Similarly, AR by, again we are defining AR by 2G tau as zeta as a damping ratio. So 2G tau, 2 zeta tau dx by dt plus x is equivalent to delta P by rho. I've done nothing new. I have incorporated two terms here. One is related to tau, which is basically your omega n, which is nothing but the square root of L by G. Similarly, we are trying to find out a damping ratio. From that, I'm trying to find out the terms in terms of your characteristic time as well as your damping coefficient, which will be in line with the transient characteristic that you have studied for your first order systems. Okay, now after solving this expression, people have tried to find out an expression over here where zeta has been given over in this form, and then rho m gh by delta p, rho m g into h by delta p, this term. They try to put it on y-axis, and t by tau, whatever the time, at what time, and what is the time constant. T by tau as the x-axis. They have given some expressions to tell you that a response of a Q-tube manometer for a step in. Okay, when you are giving a step input, suddenly you have put some pressure into that, constant pressure into that. The pressure has to be constant. So if based on zeta, what is the value of zeta here? A, that is the area, resistance, you know that 128, that expression, 2G, gravity, tau, root of L by G. Okay, liquid column by G. So if you calculate this tau, if it is 1, it follows very steadily. It goes on increasing the liquid line, and then suddenly it becomes a constant. So what do you expect after U-tube manometer when you look at this? The pressure is applied. It takes certain time until for very slowly the liquid will come down, and it kind of the liquid movement, you can see the difference in the liquids will be happening very slowly. So once by the time it reaches around 4.5 or something, T by tau, so that means 4.5 minutes or 5, you can say 5 tau. Until 5 tau of actual time, you can find out a steady value. It will not vary. They will remain the same. Are you getting me? What I'm trying to convey? So let us say that this is the U-tube. What I'm saying is whatever the difference because of the pressure applied. So after the time is equivalent to 0, t is greater than 0 once you take it. You have to wait until 5 times t, which is nothing but your tau. Sorry, you have to wait until t equivalent to 5 times the tau, that is your time constant, which is given by the root L by G, 5 into square root of L by G. You have to wait until this particular time, such that this level almost earlier when before applying pressure they are both same. Now slowly it will come down. By the time it goes up to here, this will be settled. No matter what, you are not seeing any oscillations over here. You can see here that it is happening in a very smooth way. Okay. Suppose if the zeta value is 0.5, the damping coefficient calculated is 0.5. What happens is this liquid will keep on oscillating for a few minutes. So this will go beyond this and then come over here again. There is an oscillation of liquid level. So let us say that this is the equilibrium. This is the equilibrium. There will be oscillation in between these two. Okay, first it may be here and this may be here. And then by the time it comes, the liquid may move down to here and the other level may go here. And immediately it will settle down. So there is some kind of an oscillation that you are seeing over here, right? It goes, the amplitude goes up to 1.2 times. Okay, so here it has to be around close to 1 up to 4 times. But you can see that it kind of oscillates, and this oscillations continues for some time, beyond 10. Almost at 9 times tau or something, it is kind of becoming constant. Okay, so we never know. The curve is not completely filled. So until 9 also, you are not seeing any settling down or steady state coming into the picture. Suppose your tau is equivalent to 1.5. Your damping coefficient is equivalent to 1.5. What happens? So this will come eventually to steady state. This will come eventually to steady state. It will come to eventually to steady state, but what happens is the time taken for attaining this will take a long time. Even for 9 also, it keeps on moving very slow. This level will move very slow. So now you can see after 9 also, you haven't reached the 1 position. It's not come to the steady state. So this is the problem with you when you over damp it. Okay, when you under damp it, you have 0.5, you have oscillations. When you critically damp it, it will be attaining a steady state. So this is the dynamic response of a YouTube manometer for instance. Okay, so how did you solve this expression? This you have written the energy balance basically, and then based on that you ended up a second order polynomial equation. So once you solve this quadratic equation, then we have found out based on zeta we have got different conditions or constraints. Based on that, the YouTube manometer will behave. Likewise, if you give a sinusoidal or a harmonic input, how it will behave and all that, I encourage you to actually understand that, but that will not be there for the examination. Okay, up to this you can understand. So you can see here there are 3 cases that has been developed because of the damping coefficient that comes into the picture. So now there is a question that is given here. Now a YouTube manometer which uses mercury as the manometer fluid. Okay, we have mercury, we are taking it as a fluid having density of 13,580 kg per meter cube. We have density of the manometer rho m is given as 13,580. Mu is given as, which is given by mu by rho, which is 1.1 into 10 power 7 minus 7 meters. The total length of the liquid L is equivalent to 0.6 meters. The tube diameter D is equivalent to 2 mm. Therefore, it is has to be multiplied by 0.002 meters. Okay, convert that into. He's asking us to find out the characteristic time, damping ratio of this installation, and they're asking to do the same thing with water as a manometer fluid, whereas the density is given like this and kinematic viscosity is here. What is the characteristic time? We know characteristic time tau is equivalent to root L by J. Okay, tau is equivalent to root L by G. So so you need to find out the characteristic equation. The equation written here is wrong. It should be square root of L by G. Can you check quickly? Is that the same thing? 0.6 divided by and it's product, right?
Yes, sir, it's the same thing.
It's the same thing, right? So this is missed. So first thing is we have found out. Okay, the characteristic time we have found out. What is the damping ratio? Damping ratio formula is again given. You have to find out the. We have to find out first the resistance calculation. Okay, the resistance is given by 128 mu q, that expression, right? So using that, you will find out the zeta value. So now tau has found out, and suppose the system is 0.1, it has come as to be 0.109. So therefore, it is underdamped system. So that is the first calculation. Second one is they are asking us to find out manometer liquid as water, and then they are asking to find out the same things. RH2O. This is for R resistance for Hg, mercury. So that is what my convention was. Okay, resistance of Hg I found out, and then that I have used to find out the area. Okay, pi square, and then the damping ratio I have found out. What is the damping ratio formula that we have used over here? AR by 2G tau. So tau we have found out. We have to find out what is R resistance. We have to find out, and area we know from the equation here. So when we substitute that, we will get the tau. Okay. Please solve that after I share this with you. If any mistakes is there, please let me know. Okay. So after doing this is 128 mu and q. You have to use 128 mu L, mu into L by the value is there. No, so pi d square by 4. So if you put that, you will get the value, the damping ratio value as 0.109, which is 100 amp. That means the liquid column you try to oscillate a little bit. There is an oscillation here and here, and finally it gets settled at this equilibrium position, somewhat equilibrium positions for the distance h. Okay, so oscillation will be there. The same thing we have to calculate for R, H2O, water, and then tau. And they found out that the system is very nearly critically damped. So it's almost equivalent to 0.99. That means it is almost close to 1. So instead of this liquid, if I use water for the same pressure, what is the observation that I can make? This will go very slowly up to 5 tau, around 5 tau time, 5 times the time constant or characteristic time. I can take the values because it comes to a steady state. Very easily I can take the readings. That is the point. Okay, so that is all about the dynamic responses and the response of the instrument. But I would like to go beyond the vacuum. Next topic is, according to the syllabus, is vacuum pressure measurement. But I somehow wanted to explain you the other topic also, which is like with strain gauge, how do you measure pressure? There is bellows pressure measurement. Those topics also I want to cover up. Once I cover this up, and then we will move on to the vacuum pressure measurement. Okay, so up to this I would like to finish with those topics. I would like to finish the vacuum pressure. Okay, now the next class, whatever the next class on Friday, we have the next class. So on that day we will try to finish this particular 2 topics. One is the vacuum pressure measurement, we will try to finish off, as well as there are other few devices which are helpful for us to measure pressure. Those are the 2 topics I would like to cover on those students. So for today I will stop at this point. I would like to take some questions if at all are there. Okay, so this one I will try to share with you. Okay, so please go through this particular PPTs, 2 PPTs I will share today, and if you have any questions, we will try to solve, or we can stop at this point of time. Any questions?
Yes, sir. Like we are using like what are the applications of overdamped or underdamped U2 manometer? Like where we are using overdamped or where we are using underdamped?
No. It is kind of designing. While designing, you have to understand. Suppose you are using the instrument to measure some pressure. So you should be aware that what time you have to take the measurement properly. You want it to be linearly coming, or you want it to be oscillating. So you don't want your manometer to be oscillating. Keep on oscillating with the levels, right? So you want to quickly come to a particular steady state, correct? So this tau and LG, by using that, you will be able to find out what is the diameter you have to use for the U-tube, what is the fluid that you have to use to make sure that it is critically damped. That is what my understanding is. Okay, so that it will after some time it comes to a steady state. If you look at that, the other underdamped or critically damped, if it is underdamped or overdamped, what is happening? If it is overdamped, also we are not the sensitivity of the instrument response is pretty slow. It is not coming to a steady state for a long period of time. If it is underdamped, what is the problem? If it is underdamped, we are having a lot of oscillation. It keeps on oscillating. How do you take the reading? If it keeps on oscillating, what is the correct position? You never know. Therefore, that makes things like it creates a lot of errors. Suppose you may take one value, your fellow friend will take another value. So you have to be very sure that you are making it critically damped. That means it's almost equivalent to 1. So for that, suppose the problem that I have given, in that problem, what you can observe, when a liquid, when mercury or some other liquid is used, it is coming under damped conditions. So you don't want to use that liquid. So in that sense, for the same diameter of the tube, if you use water, what is happening? It is actually critically damped. That means within 5 times its characteristic time, it will show you the steady state values. So immediately, without any error, you can take those values within 5 times. So that is the meaning of it. So how do you design it? How much time it is taking to settle down? That is a transient response. Or if the reading is changing with respect to time continuously, so which one you have to use? Okay, which signal you are actually getting out of the instrument? You never know, right? So there is a continuous change also. You cannot use a YouTube manometer. You have to go for other devices. So where also you need to understand at what time, how much time I have to wait to take the reading of the impressed input. Whatever the input that I'm giving, it is taking certain time to give an output. So what is the time I have to wait such that my output relates to the given input? Okay, when I'm taking after t equivalent to suppose 5 seconds, I have given an input, every 5 seconds I am changing the input, for example. But output is taking 5 seconds to settle down. Okay, so after 5 seconds, whatever the input that I'm giving, for initial I've given 5, and after 5 seconds I'm giving input 10, but output is showing 5. So there may not be having a proper correlation. There may be a violation of it. So now what you have to do, you should be, if you know the characteristic of it, you will understand that after this time it is showing, whatever it is showing at 5 seconds is related to the input 5. And after 5 seconds, 15, when the input is 15, whatever output is showing 10, that is related to the second at 10 seconds of time, at 5 seconds of time. So likewise, it helps you to understand or relate this. Sometimes if you don't consider how it behaves, and if you are damping it quite, you are not at all properly damping the system, what happens is immediately it keeps on oscillating. You never know what is the value, which value corresponds to what. Okay, so that is what this damping character, this transient response of an instrument has. So as an engineer, you should know that actually how this instrument will behave. What is that transient response time? Whether it is critically damped or over damped or under damped. So always you want to have as an experimenter, I want the values to be studied very quickly, right? So how do I actually damp it? What is my dampening coefficient? This is for only step input. So that means it is only changing for a certain period of time and it remains constant for that period of time. After that, again, the value will change and it remains constant for a certain period of time. Okay, so for a step input, it behaves like this. If there is an oscillation kind of a thing, how it will behave? That is your second order instrument where you have to again write down the expressions and solve it. Okay, depending on that, your equation will change, the behavior will change. So how it behaves and all is given in the textbooks. Please go through it. Did you understand, Jayesh, what I want to convey?
Yes, sir. Got it.
It helps in the design of the system.
Yes, sir.
Yeah.
Sir, also like it seems like over damping is better for our instrument. So like we are going for it, or we have some challenges in it.
You tell me, if you go for over damping, if you look at the curve, let me present this thing. Just look at this curve. Do you want to go for over damping looking at this curve? Which one do you prefer? You're an experimentalist, you want to find out. So you tell me which one you want to prefer.
Critical one is better, I guess. It will reach.
Exactly.
Yeah. Mm.
Exactly. That is what you will try to. So for doing this, what are the properties of the fluid? How much it's interact? So you have taken everything into consideration. For finding out the response, what are the things that you have considered? Just see over here. The things that are more dependent on the transient response is the transducer element. What is the element of the sensor that you are using for sensing it? Not only for this instrument, for any instrument. And then what is the pressure or how we are transmitting that signal from the sensor to the what we call output recorder or somewhere. So you have to take care all of that into mathematical form. So for this simple thing, it is nothing but what is creating, where it is sensing, this is sensing at this particular point. And this sensor will help us to transmit this when it is transmitting, some of that is also dependent on the tubing. That is your viscosity or friction. So these are the three things that are actually created. So I have taken those three things and I have done a simple analysis. From that, I will be getting the final expression. So now to get tau equivalent to 1, I will try to do, what is tau here again? You just look at the equation. Tau is AR by 2G tau. 2G tau is basically length of the, how much length? This can be varied. And G, this cannot be varied. In your position, whatever is there, that you will use. What is the diameter? You can always change this depending on what you want to remain constant. And what is your R? Your R is basically, okay, this 128 mu. Mu is what? Your viscosity of the liquid, density of the manometric fluid, and again, diameter of the tube is also in the picture. Suppose if you are taking the area as to be constant, B will become constant, but your mu and density will keep on changing. So which mu and which rho and what is the length? These are all the design parameters. So playing with that, you will try to come here. You will be trying to close to proper critically damping thing you want to have, such that after a certain period, I'm pretty sure that you already studied this. At 5 tau, 5 times the time constant of the instrument, I am getting a standard value. So it's easy for me to take the reading manually. Clear?
Yes, sir. Thank you.
Yeah, any more questions? So please do problems. See, somewhere I'll pick the problems and I'll give you. Later, don't, I mean, from the syllabus itself, it's not from, weirdly from somewhere, but I'm telling you, I cannot solve so many problems in this classroom because there's a lot of theory that can be taught. So please go through most number of problems because it's an open kind of a book, open exam kind of a book where you'll be seeing the textbook or other materials to answer. So make sure that you go accordingly. I mean, you be prepared for the this type of questions, right? So most of the questions I'm solving over here. So please, you also from your side, put some effort. After this, whatever we are teaching, it's all directly related to the theory, which you can just Google it and then write in the examination. But somehow I want you to look at the problem so that we can differentiate the students. I am of not opinion that if you are in the classroom in the offline mode, I might have given write the working principle with a neat sketch of a YouTube manometer, discuss about the dynamic response of a YouTube manometer for a harmonic input. I might have given and asked you to do that. But since it is an online, I cannot do that. So I have to do some problems. So please be prepared for some of the problems to be solved. Right. So now the time is 11 o'clock. So if you have no doubts, then I will stop this class and I will share both the link as well as the 2 PPTs. When you come for the next class, if you have any doubts, you please raise those doubts. We will try to see some more instruments. Okay, a few instruments. After this, I will be teaching apart from the vacuum measurement. Is just for your information, just to just to give an introduction to the available instruments in the pressure measurement, not for the exam sake. Okay, up to this for the exam, and then from the vacuum measurement. Okay, so that and the few things that I want to teach you are extra. Okay, that we will discuss on Friday. So please be prepared and come to the class on Friday. Okay. So if you have no further doubts, I try to wind up the session.
So one small thing regarding the TE lab submission, sir.
Karthik, tell me, Karthik.
Sir, the files. Could you please increase the file size limit, sir?
The problem is it is not in my hands actually, Karthik. The problem is that with the LMS people has actually reduced the size of it. The same problem Sardak also has told me. So I'll try to, if you give a Google form where you can actually attach these files, I think that would be better rather than following the LMS.
Because like if the record is of about 10 pages, then it's getting pixelated.
I understand that perfectly. The problem is there. So I'll try to find it. Okay, but the 4th experiment also I have given you the link, right? To upload it.
Yes, sir.
Yes, sir.
Yeah, I've given, right? No, it's not a problem. So I'll just find out and Kalyan, you were asking the last week lab recording. Is that lab recording? But I feel like it's much clearer in the video. Why do you want to have the lab recordings?
Some students are asking, sir. So, yes.
Because the last lab, it was not, I mean, it was unclear because there is a lot of other things happening. So I just didn't upload the link. So if you want, I can do that. But whatever is being taught in the lab, the same things were taught in the video. So please go through the video first. And if you still have doubts, better to go to the online video, the lab recording. Otherwise, I don't think this week's lab is required. And another thing, tomorrow there may be an exam. Okay. Have you know that, right? 4 experiments are over. So there may be a viva voce examination kind of a thing. First cycle is over. So we may be having an exam tomorrow on the whole 4 experiments. Okay.
Okay.
Not tomorrow, on Thursday's class. So Kalyan, can you inform Sarthak also about it? So that students, I will confirm it once again. Once I meet Dr. Amba Prasad sir, I will confirm you once again. But within the time, you just circulate amongst yourself that be prepared for the 4 experiments, that there will be a viva online test for the first cycle. Okay, so you may have to 20 minutes, 20 problems or so, 20 questions or so, you may have to answer. Okay, so this is the first of the time, and then second cycle 1 more test, and then final 1 more test, so that it helps us to actually evaluate the viva voce marks. Clear?
Yes.
It's like a skill test, 3 skill tests. Right. So that's it for today. We will meet you again on Friday. Okay. So these 2 PPTs I'm sharing on the sharing you to the WhatsApp, and then I'll take some time on Sunday or Saturday. I'll put everything on it. Please give me some.
Okay.
Okay. Fine. Okay. Okay, guys. Thanks for attending the class. Please take care of yourself. Bye.
Thank you.